2 times that, okay? So this is going to be 2 times the square root of 16 minus h squared. Okay. Are we clear on this? Let me do this for us. This is the base, and this is the area of triangle ADC. Okay, and this then is, and we'll dismiss with those quotations now that we've got this information. Okay, so we know that small case b is here, and so the base of this whole triangle down here now is twice that. Oh, you got the problem now, don't you? How are you going to maximize the area? Take the derivative. Take the second derivative, okay? So the hardest thing is going to be setting up the problem. Yeah, in problem solving, have you ever heard of the 4 steps of problem solving? George Polya was a mathematician that we kind of contribute to be the father of problem solving. And so George Polya came up with 4 steps. The first one is understand the problem. For us, understanding the problem meant what? Drawing the picture. Okay, what else? Knowing what an isosceles triangle is? Okay, knowing the formula. Now, the second thing is to devise a plan. So understanding the problem for us took everything we've done up to this point. Understanding that we need to use the area of a triangle. Understanding that we have a smaller triangle. All of this. Devising a plan now involves what? We got all that in place. We understand the problem. Now we just have to take the derivatives. Okay, we know our plan. I'm getting ahead of myself. The plan is, let's take the derivative of our function, and let's take the second derivative. There's our plan. The third one is actually execute the plan, to actually do it. And the fourth step is really one of the most important ones. It's look back, which is equivalent to my so what question. We get an answer. What's it mean? Okay? Did you maximize it? Did you minimize it? How would it change if I asked you to do a equilateral triangle? Would we change our plan at all if we had equilateral instead of isosceles? Now, the idea is that if I have this triangle, what if I had D and C up here? Would the area of that triangle, if I drew it up here, be different than if I drew it down here? So this is what we're about. What type of triangle will maximize, what area? And when you find the area, you're actually going to be finding what kind of triangle is going to be give you maximum area. Okay? So we have to understand the problem. When you talk to people who spend their whole life doing problems, these are people in corporations and science and all this, all they do is look at data and devise, and look at that. They spend most of almost 75% of their time is spent in understanding the problem. Once they understand it, boom, we do this, okay, now do it. Now look back, did we do what we wanted to do? Yes. But most of the time is spent in understanding it. So I don't think I need to finish this problem with you, do I? Can you take the derivative? Yeah. Can you take the second derivative? Can you find zeros? Can you look at whether or not the second derivative is concave up, positive or negative, concave up, concave down? Yeah, we can do that. If we look in the Inspire and put that into the Inspire, what would we see? Well, it'd be a little interesting because the 2's would cancel here. We would have the square root. Interesting. I don't know what kind of a graph we'd have. We'd have to look at it and see. But hopefully, we get a maximum out of it. Would you get a minimum? And just thinking about the problem, could we get a minimum area? What type of a triangle? Where would D and C be in relationship to A if you had a minimum. And what would the minimum area be? Can you figure that out without doing the math? So maybe you're thinking about that. Just a line? Is that what you said? What would the area be? The value of the area? You said 4? You said 4? Anyone want to take another guess? I say 0. Wouldn't 0 be the smallest area we could get? Can you get a negative area? No. But how would I get 0 as an area if B and C were at A? Yeah. Now, we won't take time to do it, but if you were interested in this problem, we could actually go through with our geometry page. We haven't done this. We could draw a circle. We could inscribe a triangle in there. We could measure the area. We could take the base and keep moving it up to the A and look at the area. We could do that. That would be a geometric approach to it. If, though, instead, we want to look at the graph of that, what equation would we put in here? And you're wanting to optimize? Okay, so let's do that. Go ahead and take a look at that. I want to see what you come up with. I'll keep tabs on you. Okay, Sameep and James, somehow we got a communication error. Did you log in, Sameep? Okay, James, were you logged in?
Yeah.
Okay. Somehow it's, you might need to go back and try take it off, take this crate off and put it back on. Kaylee's already tried to do the circle there. Good for you. Jenna looks like she was trying that also. The triangle there. Yeah. There's a little more that you might want to know about Jenna in order to put those points on the circle, but good for you for trying. Okay. Michelle, looks like you've got, is that the, okay. Okay. We won't look at yours any further then until you change it. Let's see. Casey, is that the equation? Whoops. I'm sorry. I can't control it. Sorry. Okay. Is that your equation there? Does that match anyone else's? That's what we want, isn't it? The original? Okay. Okay. Looks like Brandon's going about it in a different way. Okay. So now is this, tell us what this is, Brandon. Okay. So you, I assume, I don't see where you put that. Okay, you took the derivative first and then just put it in. You didn't let the inspire. Okay, so we assume that this is correct then. Okay, so you said at 0 and at 3.31. Now, what are you finding here? Maximum area? Okay. Okay, so let's see. Anyone else? Chelsea, you've got a different window on yours. Did you, move your cursor away from there, because I don't think that matches what Brandon said. Can you move the cursor? Did you do that? Okay. You've got a maximum different than what Brandon found. So someone's not. Okay. So this is why, Brandon, maybe your derivative isn't exactly correct. And so you'd want to go back and look at that. Okay, this is interesting. Who is doing this? Casey, what are you doing? You mean this thing goes up and circles around? It looks like that, doesn't it? Which would be very interesting because it means that we can actually go back in time. Interesting. Okay. But yeah, one of them is the function. The other one is the derivative of the function.
I just defined b as the derivative. That way I didn't have to go back and retype.
Okay. Okay. And what is it? Where the finger's pointing here? What does that indicate?
That's two. That's where it crosses.
And by where that crosses, you're talking about which one? The function or the derivative?
Yeah, the function. That's where it crosses the x-axis. It's the 0. That means that it's probably at the maximum.
So if you had a bigger window up here, then we would expect to see. Okay, very good. Hannah's doing some work there. Okay. So again, we haven't talked to you about this, but it's kind of neat to work with this technology because we could do it in a geometric way. And Hannah, did you find where it talked about the area, where you can measure the area of that triangle? And you have to define it as a triangle. Okay, if you only have those segments there, it's not going to work. It has to be defined as a closed polygonal shape. Okay, we could spend more time with that, but let's see if there's another problem. Andrea, you feeling better about these?
Yeah.
They're not that bad, are they? Not that bad. I know that, again, this is an area, this is something where, if you talk to some people, they just, it's like, oh, I can't do that. But it's not impossible. But let's go on. How about the second part? Solve by writing the area as a function of alpha. Alpha. What would alpha represent? And I'm going to have to, let me remove that. And I'm going to hope, let's see if I can manage this. I'm hoping I can capture all of that. Looks like I got most of it. Okay. So what is alpha in this? Let me see if I can give us some hint. There might have been a diagram, a picture of this in the book that helped us out already. And so alpha is actually defined as this angle right here. Okay? That angle right there doesn't look like alpha, it looks like something else. Let me try that again. That angle right there. So how would we now go through and solve this area looking now at the angle alpha? That's how we had it labeled before. Actually, for this, I have this side here labeled as C, and this is still B down here. If I'm going to do it in terms of alpha, I'm going to have to, we're devising the plan now, right? Okay? We're understanding the problem, actually. We haven't devised the plan yet. But I'm actually going to have to do what now? If I'm going to write the area as a function of alpha. I've got to use a different bit of information. If I want alpha, I'm going to have to use what? Yeah, trig of some sort. Yeah, it's either going to be sine or cosine or something. So maybe we know this is 4 plus h, right?